and welcome to Acoustics Derivation. In this video, we will be discussing and deriving energy density in a sound wave. But before we begin, what do I mean by energy density? Well, energy density, which we will denote as epsilon, is simply energy per unit volume. So we're using density to indicate per unit volume. In other words, we want to find the energy per unit volume of a sound wave. Well, if you think back to your freshman physics days, we know that energy can be kinetic and potential. So kinetic energy and potential. So to find the kinetic energy in a sound wave, it's rather simple actually. The kinetic energy is so if you think just in general, we think of kinetic energy as 1/2 mv squared, or m, of course, is mass and v is velocity. Well, we want energy density, so we need to divide that by volume. And if you do that, you simply obtain 1/2 rho u squared, where u is the particle motion, the particle velocity, I should say, and rho naught is, of course, density. So if you would see, if you multiply this by volume, you obtain just kinetic energy. I should note that u squared, u squared is u dot u if you're not if the motion of the particles is not collinear with, for example, an axis or only in one direction. So if you represent your particle velocity as a vector, then u dot u is u squared. Now, potential energy is a little bit more complicated to determine. To do so, we will consider a volume element that has some initial volume V naught and some perturbation pressure of zero. P is equal to zero. So, for example, you could think of this as a control volume at standard temperature and pressure. So there's no deviation from that standard pressure. Now, let's suppose we apply, draw this a little bit smaller. Let's suppose we apply some pressure, some extra pressure to this volume element. We know that it's going to, the volume element is going to shrink in size with the pressure applied. Well, if we think about the work being done on the volume element, the potential energy of the element is negative V naught to V, the integral from V naught to V of P dV. Let me write that P a little bit. So again, this is the work, and the minus sign is because the potential energy increases for uh, dV less than zero. Well, if this is just your potential energy, it's very easy then to solve for the potential energy density. You simply divide by your initial volume. Why the initial volume? Well, we're assuming the change in volume is very, very small. So it is okay to assume to divide by just the initial volume. Now, this is a perfectly valid, if you would, solution for the potential energy density in a sound wave. However, it's not very helpful or illustrative. So we need to do some more manipulation. To proceed, let's consider the conservation of mass in this element. Well, there's no flow of mass in and out of the element, and so the mass which we know is rho times V. That's constant. There's no mass flow. We can rearrange this equation to say that the volume um, is mass over rho, so mass over density. If we take the derivative of volume with respect to density, we have dV du rho is equal to negative m over rho squared. However, we note that V is m over rho, so this is really negative V over rho. We can move the d rho to the other side and find that dV is equal to negative d over rho d rho. Okay. So again, we're considering a very, very small change in volume, thus a very, very small change of density. So we're going to undergo the process of linearization. So we're going to let the volume V be your initial volume V naught plus some change in volume. So if we're looking at this volume, let's go up a little more, this volume element, or I should say the resulting volume element on the right here after you've applied your pressure, we note that we started at our initial volume and we've changed a little bit to obtain our current volume. So this change is V prime. Likewise, we can have that density is your starting density plus some small change in density. So we're going to linearize this equation here. And to do so, anytime we have a perturbation quantity, so with a prime, if you have two perturbation quantities multiplied together, then we consider that a nonlinear quantity, and so we'll ignore it. In other words, a small quantity times a small quantity is a very, very small quantity, so we just let that, we assume that to be zero, essentially. When we undergo that process, we find that dV is equal to negative V naught over rho naught times d rho prime. And you might be asking, why did I linearize it in this particular fashion? Well, you'll see in just a moment. To proceed, we need to recall the linearized state equation. So we have the linearized equation of state. Which says that your perturbation pressure is equal to the small signal sound speed squared times your perturbation density, which can be rearranged, and if you take a derivative, you find you have d rho prime is equal to dp over c naught squared. Or I shouldn't say a derivative, you take the differential, I should say. Well, I've linearized this equation up here because I want to obtain dV in terms of dP. So we can substitute it in and then take our integral of P times dP. So that's the reason I linearized it in this fashion. As such, we can say that dV is equal to negative V naught over rho naught C naught squared dP. Okay, so I just plugged this d rho prime into there, and this was the result. Okay, so now recall this equation. I will circle it in a different color here. Recall this equation, and we're going to plug in dV, the result we had for dV, into this. So we have that the potential energy density is 1 over rho naught C naught squared times the integral of 0 to P prime dP prime. Why am I doing P prime? Because just we if you're integrating from x dx and from 0 to x, you need to have a dummy variable such as x prime. So that's exactly what we're doing over here. Also, the bounds changed on the integral. We went from v naught to v, and now we have 0 to p, which again we call, sorry, this should be p, not p prime. So 0 to p. Why? Well, this was the pressure change that corresponded to the change in volume. Remember, we said that little p was equal to 0 originally, and we applied some pressure, and then that p was greater than 0. So we went from 0 to p. Okay. Well, now it's a simple integral, the integral from 0 to p prime dp prime. The result is p squared, over 2. So we have the potential energy density as p squared over 2 rho naught c naught squared. Okay? Thus, now that we have, if you recall, we have the kinetic energy density and we have the potential energy density, we simply just add them up to find energy density of the sound wave. Energy density. We have that the energy density, like I said, you just add them up. So you have the kinetic energy density and the potential energy density, is p squared over 2 rho naught c naught. Let me write this in the order they showed up. So we have 1/2 over rho naught u squared. So that was the kinetic energy density plus p squared over 2 rho naught c naught squared. So this is your energy density in the sound wave. Now, we often like to consider plane progressive waves because they're easier to work with. And if we do so, we obtain a special result or a unique result, I should say. So plane progressive waves. If you recall, the relationship between pressure and particle velocity for a plane progressive wave is P is equal to rho naught C naught U. Or we have that U is equal to P over rho naught C naught. If we plug this in, we note that we still have the energy density as P squared over 2 rho naught C naught squared. But then if you plug U squared, I should say, into U squared for the kinetic energy density, we see that the kinetic energy density is also P squared over 2 rho naught C naught squared. Well, then we say that simply epsilon is 2 epsilon sub P, so the energy density is twice the potential energy density, which is simply P squared over rho naught C naught squared. So this, once again, is the result, the energy density for a plane progressive wave. So it's a bit simpler. So that concludes our discussion in this video on energy density. In the next video, we will talk about something known as the acoustic energy corollary. We'll derive it and we'll talk about it. And that relates the energy density in a sound wave to the intensity of a sound wave. And so we'll see how those are related and we'll, like I said, we'll discuss them. So that concludes this video. Thank you.